Hi there, I am Thomas Lebert, co-founder of CMARC in the Maldives. In this presentation, I will expose how different elements cycle in our biosphere and explain why this understanding is paramount in order to control climate change and sustain an ever-growing human population. First of all, I think we have a puzzle, which I summarized in this equation. On land, there is no biomass before the Precambrian, and from this state, it seems that the application of an operator such as described by the theory of Darwin cannot explain the accumulation of land biomass. The evolution of life described is purely formal and not material, the pre-existing biomass providing the atoms that make up a given organism is taken for granted. Apart from oxygen and hydrogen, which are abundant due to the prevalence of water, the main atoms we find in biomass are the carbon and the nitrogen. In the human body, for example, we have around 23% carbon and 2.6% nitrogen. While looking at the different parts of our biosphere and their carbon or nitrogen content, it appears that these two elements are quite rare and only concentrated in biomass. We make a difference between the inert atmospheric nitrogen and the fixed nitrogen, which is readily available for the living organism as nitrate and amino acids in proteins. Because there is a limited stock of carbon atoms, it makes sense to build a biomass in order to reduce the carbon dioxide content of the atmosphere. Rather than sequestrate the carbon, this would recycle it and hold it as usable biomass. Primary biomass creation involves photosynthesis, which enables plants to use light energy to create sugars and oxygen from carbon dioxide and water. But for organisms to develop, they will also require some nutrients and some space. To keep things simple, we will focus on the fixed nitrogen as the main nutrient and assume that the others are not limiting. So let's have a look at the main characteristics of these two elements. Carbon is available everywhere in more than sufficient quantities for photosynthesis, both on land as gas in the atmosphere and as dissolved carbon dioxide and bicarbonate ion in the sea. Fixed nitrogen, on the other hand, is subject to losses. When there is no oxygen, denitrifying bacteria unfix the nitrogen and send it back to the atmosphere as nitrogen gas. This is what is being practiced in our sewage treatment plant. In the presence of oxygen, it oxidizes in nitrate through both biological and chemical processes, and in this form dissolves in water and is transported back to the oceans by runoff. It therefore appears that for its abundance to be maintained on land, the fixed nitrogen has to be constantly brought back up against gravity. In this painting, Peter Sawyer shows us what Earth would have looked like before the Precambrian. We have life in the oceans, and in particular the stromatolites, which are said to be responsible for the release of oxygen. Multicellular life, using oxidation of organic compounds as an energy source, has emerged in the ocean, but there is no terrestrial life yet, presumably because there is no fixed nitrogen on land. The primitive animals adapted to the coastal environment and spread the fixed nitrogen on land through their dejections and the decomposition of their bodies. Thus, the conditions were met to create primary biomass on land, and the plants adapted to the terrestrial environment. They thereby fixed the nitrogen, geographically this time, in a form consumable by animals. This enabled their migration inland, and step by step, the terrestrial environment is colonized. In the overall development of life, we can therefore see that the primary function of the animals is to move and spread the fixed nitrogen, when that of the plants is to prevent it from flowing down back to the oceans. Instinct is a powerful force driving this movement, starting with hunger, which causes animals to ingest biomass and spread it around. This avoids high concentrations and anaerobic processes and enables life to constantly recycle fixed nitrogen. Therefore, it is legitimate to use any form of biomass or excreta to promote biomass growth. More than anything, we need to provide space and nutrients in order to build up biomass. On land, unfortunately, there is very little space left, as we have developed most of it for agriculture and cities. Deserts have too little water, and we are trying to preserve the rest. In the oceans, we have a much larger space, with holding and buffering capacity. The fact that it is three-dimensional and not b-dimensional like the surface of the land eases the space constraint. Another difference is that there is little large primary producers, and the mobile animals have to fulfill both the function of dispersing the nutrients and storing them in their bodies. By their life history, they effectively maintain the nutrients in the photic zone. We have previously determined that the nitrates would constantly flow down to the oceans, but this is unfortunately confined to terrestrial waters and the coastal areas. Here we take a look at how it is distributed along a depth profile in the open ocean. In this typical profile, we have very little nitrogen in the first 100 meters. This is due to its consumption by the primary producers of phytoplankton. In this zone, there is an important mixing of water, and its oxygen and carbon dioxide contents are in equilibrium with the atmosphere. Below this, the photosynthesis is too weak and oxygen creation is non-existent. The oxygen is depleted and anaerobic bacteria consume the biomass falling from the photic zone, causing an accumulation of nutrients at around 1000 meters. When these nutrients come back to the surface, they will promote the ocean biomass productivity, but given the timescales of Earth cycles such as the thermohaline circulation, it could take hundreds of years before these nutrients come back to the photic zone. Below this, there are some more stagnant waters, mostly coming from the sinking of cold waters at the poles, and therefore they are quite rich in both nutrient and oxygen. To promote ocean productivity and the abundance of the fish in the sea, it doesn't seem necessary for us to wait for the nutrients to come up from the depth, as we could very well dilute them at the surface. This agrees with different ocean fertilization techniques using urea or iron compounds which have been proposed. Let me summarize the step of this shortcut. Organic matter can be recycled provided we give it water, light and space. On land, there is little appropriate space available, while at sea, we have large volumes of unused space with large holding and buffering capacity. Organic matter sources can be primary biomass or animal excreta. It would be better to recycle the fixed nitrogen from organic matter in biomass rather than to send it back to the atmosphere through anaerobic denitrification. Phytoplankton production can be increased if we add more nutrients to the photic zone. By fishing, we are in fact mining the fixed nitrogen from the oceans because the fish are like nuggets of fixed nitrogen previously distributed over large volumes. Having mined the atoms that make up the fish, how can we really expect to have more fish? You can already see by now why putting biomass in the photic zone may be a good solution to our current problems, and I will now present 3 ways in which I think this could be carried out. The first method would be to sink biomass into the deep oceans. The atoms would be stored for a long time, and even possibly in time create fossil fuels. But it gets rid of the nitrogen as well as the carbon, and therefore would be better done with organic matter having little nitrogen, such as wood. This wood could come from green wastes or managed forests. It could benefit the growth of deep ocean marine life, or encourage phytoplankton growth when coming back to the photic zone. It would necessitate an increase of boat traffic and extension of harbors and coastal facilities. The second method would be to dilute animal excreta rich in fixed nitrogen in the ICs. This would decrease the degassing of fixed nitrogen consumed by humans and domestic animals and would also lower the cost of water treatment. It raises the problem of industrial wastewaters being mixed with residential effluents, as well as the disposal of certain non-biodegradable molecules. Saltwater in itself is toxic for most bacteria found in excreta, but the release would be preferably done at the surface to kill off remaining bacteria by UV irradiation. At the same time, it will increase the dilution by wave action. These two methods may appear reckless and would necessitate some specific infrastructure development. The last method presented here has less of this drawback. It is based on floating microphytes, which utilize the excess nutrients present in rivers and lakes for their prolific growth and, in many cases, are thought to be invasive. Let's see what's happening in California.
My name is Rick Hatton, and I run a company that takes aquatic weeds out of the water. For the Port of Stockton, we're removing the hyacinth that you'll see out there in the water floating. Water hyacinth is a plant that floats. It does not have roots that go down and touch the sediment, the dirt. And that's why you'll see it moving all over. As the tide comes in and out, as the winds blow, this plant just floats along. To take the hyacinth out of the water is something called an aquatic weed harvester. You can see one of them over here on my left. So we go through the water, and any plant that's in the boat's path, it gets gobbled up. It comes up a conveyor belt onto the boat. It holds about 200 to 250 cubic feet of plant. When the boat's full, then we come into shore, we throw it into a large pile and just let it rot. They want us to also go way downriver to downtown Stockton. It's clogging it. It looks terrible. The port wants to be a good citizen of this city and has already authorized us to go down there and clean that area.
Water hyacinth and water lettuce have some of the highest growth rates of all plants. They develop thanks to the overload of nutrients in our freshwater bodies. This overgrowth can be used as an organic matter source to fertilize the oceans. It can be carried with little energy by river flow to the mouth of the river. Once there, it can be released when the wind is offshore and will disperse and reach the high seas. Saltwater being toxic for this plant, it will float on the surface for a couple of days, will be partially consumed, entering directly the food chain, and then sink to the bottom of the oceans. It would avoid costs and measures taken for its eradication, remove excess nutrients in freshwater bodies, and avoid eutrophication. Eventually, it would provide a biological filter preventing potentially harmful compounds to be released to the oceans. The implementation of such methods would need to be backed up by an appropriate carbon credit scheme, whereby a tonnage of carbon equivalent to that contained in the disposed biomass would be converted into marketable carbon credits. As the biomass is directly measurable, these carbon credits would be easy to account for. It would provide a long-term storage for the carbon at the bottom of the oceans, but also enable some of the fixed nitrogen to be recycled in biomass, and this would help us to sustain our growing population. Being respectful of the organic matter cycling, they could solve more issues than just climate change and help us reduce our overall dependence on fossil fuels. Some of the costs encountered for dealing with different environmental problems could be reduced. I wanted to finish this presentation with the trilogy of the Earth by Suzanne Duranceau, where the artist presents first some type of paradise lost, as it would have been when governed by the instinct. In the second, she represents what is probably in store for humanity if we stick to our errors. And in the last one, the Earth seems to be managed more rationally, but personally, I am worried that there are not so many animals. What is represented here is the epitome of the Darwinian struggle of the fittest, the triumph of a certain idea of reason over instinct, when in fact a reasonable inquiry into the development of life on Earth tells us the story of an implicit collaboration between species to mobilize as many atoms as possible. Thank you for listening.